join. If you get the recording window, please press yes so that we can go ahead with the talk. So this is one of the seminar series we envision to bring forward advanced imaging, image analysis and biological applications of such techniques. And Andy York is our inaugural speaker here. Andy and I go around 2011 is when we met in the physiology course. We both wearing the same t-shirts, as you can see. So Andy was a postdoc at that time with Harry Schroff at NIH. This was the time when the light sheet had not hit the fan yet. But in the following years, light sheet technologies have exploded, and Andrew, after contributing to ISIM, which is instantaneous super resolution technologies, he's moved on to light sheets now. After his postdoc, he interviewed at Google and then rejected their offer. And then Google chased him up and said, look, we want you here, do whatever you want. One of the things that this has allowed Andy to do is to challenge the game of publications and disseminate technologies and knowledge very freely and openly, without going through the publications and the review process, et cetera, et cetera. So without further ado, I'll let Andrew share his screen and take over.
Beautiful. I'm super happy to be here. And as I mentioned a minute ago, I'm really happy to see a bunch of folks in the audience who I believe are kind of champions of open science and open, open source code and things like that. And I believe a lot of the folks here have written code that I'm very happy to use. Can everybody hear me all right? Are my levels okay?
Yes, all good.
Okay, and can you see the slides that I'm sharing over here?
Yes.
Okay, great. So I'm going to be looking at my slides. I only have the one monitor. So if no one interrupts with a question, then I'm just going to be talking to the wall in my office for the next 45 minutes. So please make this a bit more participatory. I'd appreciate that. And then I'm assuming that most of the folks here are perhaps biologists with an interest in microscopy, or perhaps physicists with an interest in biology. So that's kind of who I've targeted this at, but use questions to direct me if I can be more productively focused. All right, so I guess with that assumption, so if you are who I think you are, then we kind of share the same life mission, right? Which is discover something interesting or useful and share it with the world. And the hope is that you have impact, and everybody has to define impact for themselves. But for me, and probably for you too, the definition is simple. It's the reason you share your discoveries is so other people can build on top of them. And in turn, you can build on top of their discoveries. And it's kind of a wonderful cycle. There's, I think, an analogy to be made to the world of open source software. And you guys might agree with this. If there is a aspect of your work which is critical to your success, and I'm talking about dissemination. So my training's physics, my field is microscopy, but my identity is to try to be an inventor. So I try to invent things. And if nobody uses anything I invent, then what good are my inventions, right? So dissemination is this really critical ingredient on my path to impact. And you guys have probably heard the phrase, don't outsource your core competency. So dissemination is one of the core competencies of my life's mission. And I think it's very typical, almost universal in the scientific field, to completely outsource one's dissemination. And I'm here to argue that maybe that's not the right way to do it. Maybe we can do better. DIY, I mean, do it yourself publishing. I happen to publish on GitHub, but I don't particularly care about the format, just kind of the goals. Now I got this social message, but I was going to tell it, based on concrete technical stories. And I'm guessing most of the folks in the audience here are familiar with structural illumination microscopy. Just somebody give me a shout just to confirm that.
Yes.
Okay, great. Okay, so I say structural illumination microscopy, and most people know what I'm talking about. And just very briefly, on a regular microscope, if you zoom in, eventually things start to look blurry. On a structural illumination microscope, you can zoom in about twice as far before things start to look blurry. Now, there's lots of microscopes that improve your resolution compared to the traditional diffraction limit. But what I like about structural illumination microscopy is it gives you this moderate advantage, this nice advantage in some cases, and it doesn't make you pay very many taxes to get it. So it's a trade-off, but it's a pretty reasonable trade-off in many cases. I'm going to try to make the case that if you do it right, you can get this trade-off with no drawbacks. And I'm going to say that's kind of a good path to impact, as an advantage with no drawbacks, right? So what do I mean by do it right? So now just a moderate technical story. When I say resolution, I just mean how far can you zoom in before things start to look blurry. Now, just because your image looks blurry doesn't mean your object is a blurry object. You have good reason to believe your object is composed of intricate structure. But of course, you're not directly visualizing your proteins in your cell typically, unless you're very lucky and you study something that happens to be fluorescent. Usually you study them indirectly. You attach a tag to your protein of interest, and your tag might be the classic green fluorescent protein. So you're not imaging your protein, you're imaging your tags. So if you're trying to look at structures finer than the packing density of your tags, that's going to be tricky. But of course, your tags might be a few nanometers across, but due to how light works on a conventional microscope, they will appear to be a couple 100 nanometers across. And this is a very straightforward truth about how light works: diffraction. So how tightly can you focus light? This is kind of interesting, though. I want to emphasize that the question, how tightly can you focus light, and how far can you zoom in on an image before it gets blurry, are different questions. And I believe it was more or less implicitly assumed for a couple centuries that those were the same question. And then some innovations over the past couple of decades have really highlighted that inference is distinct from focusing. And one of my favorite papers that makes this point is, one of the original publications on structured illumination microscopy, clearly making the point that how tightly I can focus light is related to, but not synonymous with, how far can I zoom in before things look blurry. This kind of came to my attention when I was a postdoc with Hari at the NIH. A biologist came to me and he says, "Hey, physicist, I got a problem. I got a theory that says something about the distribution of proteins at the division septum of, I think it was Bacillus subtilis." He says, according to my theory, I predict that there should be 2 rings at the division septum. It's curvature sensing protein localizing to the regions of extreme curvature. So he says on either side of the division septum, there should be a ring of protein. And the competing theory predicts a single ring. So that's a very straightforward experiment. Look at it on a microscope and count the rings. But the problem is the microscope gave an ambiguous answer. There's one interpretation, which this is a single ring. There's a second equally valid interpretation, which this is 2 rings, which are closer together than about 100 nanometers. And if based on what he knew about the septum, those both interpretations were consistent with this data. So he decided to use structured illumination microscopy, invented about a decade prior. It's pretty quick description to say that you take a series of images of your sample, 9 images or 15 images are pretty typical, 25 images if you want to go crazy. Each image, you illuminate your sample with a different stripe-like pattern, and you rotate your pattern and you shift your pattern. And then after you've acquired, let's say 15 images, you do some math. This is a cartoon version of the math on the page, but this is actually reasonably accurate. And the hope is at the end of the acquisition and the mathematics, you have recovered an image which is about twice as good as what you would have gotten on a normal microscope. Now, just to show you kind of a aesthetic evidence for this claim. So here's a conventional microscope taking a nice picture, and here's a structured illumination microscope taking a picture that maybe looks even better. But then, of course, for my colleague, he didn't just want images that looked more aesthetically pleasant. He wanted images that answered his question. And in this case, this is what I'll call a Goldilocks problem. It's not too big that you don't need extra resolution, and it's not too small that a factor of 2 is worthless. It's just right. Structural illumination microscopy gave him just enough resolution to convince himself that indeed he had evidence that there were 2 rings consistent with his belief. So I thought that was pretty cool. And by the way, at the same time, we were trying to answer the same question with localization microscopy and totally failed for a number of technical reasons. And this really drove home for me a lesson about offering advantages without offering drawbacks. So just a brief intermission. So I did not really explain in a technical sense what structural illumination microscopy is, and I won't. But I do want to show you. I might stop sharing just for a moment. You guys can perhaps see my face a little bigger now. This is a transparency, back when transparencies were a thing, with a bunch of vertical stripes on it. I don't know if you can see them on my lousy webcam, but there's a bunch of vertical stripes in this transparency. Some of you know what's coming here, right? And this is a piece of paper with similarly a bunch of vertical stripes on the piece of paper, right? Now, individually, there's a filtering between these stripes and your computer screen, between my webcam and whatever image compression algorithms, you probably can't see stripes on the paper. You can probably just see maybe uniform gray, right? Or maybe you can just resolve the stripes. But here's what I want to show you is when I take these two stripe-like patterns, you can pretend one of these is your sample and one of these is your illumination, and you overlay them, you start to see some very smooth structures, which you can do inference on to reveal the presence of these fine structures. I don't know if you guys can see there's a horse there. And the point I want to make is that you might have been able to see that there was a horse there, but you don't have any evidence that there was any structure whatsoever if you weren't overlaying a grid of fine stripes. All right, so back to sharing the slides. Okay, so the mathematical connection between that demo and structural illumination microscopy is a fun walk. But if you want to play with the code that made those printouts, my colleague Benjamin Cooper put up a GitHub repo. I suspect other people have done the same demo. Anyway, so just kind of in summary, for traditional structural illumination microscopy, double the resolution and not too many drawbacks. There's a trade-off, but for my colleague, it was a great trade-off. It wasn't great for looking at really thick, densely tagged samples because you can computationally reject out of focus light, but the noise from that out of focus light is still present. So it's not as good as a confocal for looking at thick things. It is a computational technique, so it effectively includes a deconvolution step. And deconvolution has a different set of artifacts. I'm not saying better or worse, I'm just saying different compared to a conventional microscope. And all measurements have artifacts. The definition of a bad artifact is an artifact that you mistake for signal. So it's kind of an obstacle for new users to use structural illumination microscopy is you have to retrain your eyes to see what are artifacts. But for me, kind of the worst drawback of structural illumination microscopy was as your samples got dimmer, if you're trying to image proteins expressed at native levels, your signal noise ratio can get pretty lousy. And in my hands, at least, traditional structural illumination microscopy fails catastrophically for low signal levels. Basically, your ability to judge where the stripes are is critical. And when that disappears, you don't even really get an image anymore, or it's an image, but it's garbage. Anyway, just saying it's a good trade-off, but it's still a trade-off. Now, I said, back at 20 years ago, structural illumination microscopy was invented. 45 years prior to that, it was known how to double the resolution of a microscope. The guy that invented confocal already knew it had twice the resolution of a wide field microscope. It's kind of cool that he saw this coming. So just a little technical story about why that was true, but why that was also technically irrelevant. So imagine a terrible microscope, a microscope where I illuminate the whole sample like a wide field, and I use a system of lenses just like a wide field to form an image on my camera. But it's a terrible microscope because I've ripped all of the pixels off of my camera except for one. And I'm going to call that one pixel a pinhole. And let's suppose I take a picture by moving my object through the illumination region. If you might see the signal on your detector might look like a Gaussian, for example. The width of that Gaussian will be a couple hundred nanometers, and that'll depend entirely on your emission path. It has nothing to do with your excitation light. You can imagine another terrible microscope, which is kind of that same idea backwards. No information from the emission path because you pull out the lenses. You just collect all the light that comes out of the sample. You get all your resolution from how you focus the excitation light. If you can focus it down to a tight little spot, the width of that spot will kind of determine the resolution of your system. So one of these says that each of these signals answers a question. And one, it's how likely are your photons to be detected as a function of emitter position. The other says how likely are your fluorophores to be excited as a function of emitter position. So confocal does both. That's why I told you that story, so I could tell you this one. The signal you'd see on a confocal microscope would be the product of those two signals. How likely were you to be excited as a function of position multiplied by, given that you're excited, how likely were you to be detected as a function of position? So as you guys might imagine, the product of two Gaussians is skinnier. So a formal way to say that is the confocal point spread function is the product of the emission point spread function and the excitation point spread function, and the product of two skinny lumps is a skinnier lump. Now, earlier I said a single pixel on the camera. I also refer to that as a pinhole. If you use a very small pixel, that's great from a resolution point of view. But if your detector pixel or your pinhole is much, much smaller than the image of a glowing object, you end up discarding most of the light that exits the object, like more than 90% of your light, for example. So it's traditional in a confocal microscope to use a much larger pinhole. And there's an analogy you can make to using big chunky pixels on a camera, you probably know that if you use big chunky pixels, the pixel size can limit your resolution. And that's the case in a typical confocal microscope. So if you use a very small pinhole and throw away most of your light, you get great resolution. But it's much more typical to run with a big pinhole, get much more light, but sacrifice one of those two skinny Gaussians, turn it into a fat Gaussian. So the product of a fat Gaussian with a skinny Gaussian is pretty much the same width as as the skinnier Gaussian. You don't get much resolution improvement. So you can use a big pinhole, get no resolution improvement, or you can get this resolution improvement Minsky was talking about at the cost of tons of your signal. In most contexts, I would not advise a collaborator to make this choice, but it's technically true. So small pinhole gives better resolution, worse signal. I told you a bad idea, so now I can tell you a worse idea. If you misalign your confocal microscope, scoot your pinhole off to the side, you throw away even more of your light. And you'll shift your image because the product of two Gaussians that are shifted with respect to one another is intermediate in between the two Gaussians, right? So if you shift your pinhole by X, you shift your image by X over 2. You trash your throughput, way fewer photons. But here's kind of a funny truth. What you don't do is degrade your resolution. If your PSFs resemble Gaussians, it's rigorously true that the product of a Gaussian with a shifted Gaussian, the width of the result does not depend on the shift. So you don't lose any resolution here if your PSF kind of looks like a Gaussian. You just shift your image and throw away tons of photons. So why did I tell you a bad idea followed by a worse idea? And the point is it leaves room for an actually good idea, which is kind of fun how that works. So here's a kind of a zoom in looking at the single detector pixel, a single pinhole in your confocal microscope. The blue is showing you the pinhole, the green's showing you where the photons might land. You can shrink your pinhole down and throw away all the photons, and your resolution does get better, like I said. And then you can make an even worse decision, misalign your pinhole with your excitation spot, and throw away even more of your photons. But your resolution doesn't get worse. Your image just gets dimmer and scoots off to the left a little bit. So here's the fun part. If you put a second pinhole where the first one used to be and send those photons to a separate detector, you get two images, and the individual images have the same resolution, that same good resolution from that small pinhole. But you start to claw back some of those photons you threw away when you were chasing resolution. And there's no reason to stop it, too. You can put, I should emphasize, these images are the same resolution, but they're not registered. You have to shift one image to get it to match up to the other image. So if you register your images, if you shift one image to match the other prior to summing, you get back some of your precious photons and you preserve all that good resolution. And there's no reason to stop it too. So you can put another pinhole, makes a shifted image, but if you computationally register your images prior to summing, put another pinhole, put all the pinholes. So here's a system where you're collecting tons of images simultaneously, computationally registering those individual images, and you're getting all the resolution of a small pinhole and all the precious photons from a large pinhole. This is kind of a cool idea. This is an old idea. 30 years ago, this was invented, this was disclosed, and now I'm kind of getting back to a social point. Colin Shepard's brilliant, had a great idea, and really dropped the ball disseminating the idea. And I don't mean he didn't communicate it. He published it in a journal just like you're supposed to. But somehow, I wasn't there. I was a child, a young child. Nobody built one. So 20 years passed before this great lab in Germany independently rediscovered the same idea, and unfortunately did not give appropriate credit to Colin Shepard, but they've corrected it since then. They know now. They discovered the same idea, but they built it. They showed it worked, and they got it into a good physics journal. There's a reason this is not in a biology journal. It's because the instrument is punishingly slow. It takes like 15 seconds to tile, or 15 seconds or minutes. Anyway, it's a really slow instrument, but it proved the principle, and arguably more importantly, it inspired a bunch of modern physicists to try out the idea, and one of them was me. So I look at this instrument and I say, that's a cool idea. I don't want to use that microscope, but maybe I can make it go faster. So instead of using one spot and taking minutes to tile, I think it was 15 minutes to tile a 5x5 micron region, which is really slow and really small. So I decided, instead of one spot, let's use 1,000 spots and make it go faster. So this was cool. We acquire a series of images as you scan an array of spots through the sample. And you get about the same resolution as regular structural illumination microscopy. And this is 10 years after structural illumination microscopy was invented. So what's the added value? It's simple. It's just by using an array of spots instead of an array of stripes. Most of the out of focus light lands on your detector in between the spots, and you can very effectively reject the noise due to the out of focus light, just like a confocal. So it's basically structural illumination microscopy that's about an order of magnitude slower, but it gives you better sectioning. So this was enough to publish, and that was nice. So you acquire images for about a second. You take about 200 images in my case. You process your images for a couple seconds, and you get a nice section image that can work in thick samples, and the resolution's doubled. So this is my entry into the structural illumination space, another trade-off. And in some cases, a really good trade-off. In some cases, not so much. I told you that story so I could tell you this one. The way it was published was very physicsy. They publish an equation. And an equation is a great, accurate, compact way to communicate, but it's not really how I think by default. I'm capable of using equations, but it's not my preference. So as I was working through the paper and re-implementing Mueller and Enderlein's idea, I, as wherever possible, was thinking in pictures instead of in equations. And it turns out that there's a very straightforward graphical interpretation of the integral on the previous slide. You're scanning an array of spots through the sample, taking a picture for every position of the spots. And for each photon you detect, you know the detector pixel it landed on, which suggests that the fluorophore was probably centered there. And you know where the excitation spot was centered in the sample, which suggests perhaps the fluorophore was centered there. Now, the truth is probably somewhere in the middle, right? So you split the difference. You put the photon in between where you detected it and where you excited it. It turns out that has a very simple graphical interpretation. It's just shrinking. So I was really happy when this came to me because it made implementing it much more straightforward when I had a concrete graphical interpretation. Oh, and somebody just confirmed that I'm still speaking to other humans. I haven't heard a noise for a while.
Yes, Andy, you're fine.
Solid. Beautiful. Cool. Appreciate it. Got lonely. Okay, so this concrete graphical interpretation, it's just shrinking. I was kind of happily explaining to somebody, I said, oh, I use Python to do my image processing code, but if you give me enough time and enough patience, I could do this in Microsoft Paint. I'd literally crop out each image, shrink it, paste it back into the image, and add it up for a series of such images. And I was explaining, we could do this with a bunch of undergrads in Microsoft Paint. Well, we could do it with pieces of glass and lenses. And after I said it out loud, a couple beats passed before I was like, oh, that's actually useful. So every one of those processing steps I just described, you want to throw away the out of focus light in between the spots. You can do that with a mask. You want to contract the image of each spot by a factor of 2 towards the center. You can do that with a microlens array. You want to sum up the resulting processed images into a super resolution image. You can do that just by leaving a single exposure of your camera going while you accumulate photons. And this was pretty impactful, much more than turned out to be a better idea than I got lucky is what I'm trying to say. Because, not only does it take a couple seconds on the computer to process the data, and, maybe we could make that faster, but it takes a couple nanoseconds for the light to process the data. So I'd say that's preferable. But maybe even more important, it takes, in my hands, a full second to acquire the hundreds of images that went into the hundreds of camera exposures that go into one super resolved image. But in this case, the data is already processed by the time it gets to the camera. So you only need one frame. So this is pretty cool. That means not only are you, infinitely faster for the processing, you're 2 orders of magnitude faster for the acquisition. So all of a sudden, you're not a trade-off anymore. You're just better. Better than spinning disk and focal microscopy, which is a really trusted, proven, useful instrument in the core facility. So if you believe me, and whether you do or not, just pretend you believe me, this is the first super resolution microscope with no drawback. And that's great. If that's true, and it's just a spinning disk that's got twice the resolution, that's nice. Does it matter? And how long before we can tell? And that's kind of where I'm going with this story. How long until impact? So you guys know when you got a good idea, the most important thing to do is keep it a secret. It's a disaster if anybody finds out, right? So I write an email to my boss, and I start working my tail off trying to implement the thing. Got the first images about a year later because I had good funding and good health and good luck. And now, of course, how can anybody tell if this is a good idea? Of course, you have to judge if it's a good idea by what journal it gets published in, right? Because if it's a bad idea, it should go to a bad journal. If it's in a good journal, it must have been a good idea, right? So I got to spend a whole other year getting all the nice time-lapse imaging and the 3D surface renderings and the fly-throughs and stuff so I can get into a good journal. And we bounced off Science and we bounced off Nature. And we spent months keeping the idea a secret, bouncing off different journals, got it into Nature Methods. Very, very happy that happened. And I think there's a temptation when you publish a paper to say, I'm finally done. Try to move on to the next project. But think about that. This is the first public disclosure of the idea. Preprints weren't so popular back then. This is the very beginning. This is the first point where it is not literally impossible for me to have impact. So for my field in particular, reproduction is pretty nice. Somebody else building the instrument and showing that it works is an important part of, convincing folks you weren't full of it. So we got our first nibble for reproduction the next year. And particularly in my field, to have real impact, it's nice to have commercial dissemination, commercial distribution. We got our first nibble that same year. I was very impressed with the commercial distributor that the product came to market by 2015. The engineer that did this did, I think, a great job. But if you walk in any core facility, you look at a spinning disc confocal microscope, it's probably a Yokogawa. So it's particularly gratifying for me to see Yokogawa finally making their flagship instrument include this innovation. I think it's available sometime in 2019. So is that impact? And I think the interesting point is so now you can buy one, and some people have, but impact is still a couple more steps off. People have to use it. It has to actually be useful. It has to actually show them something they couldn't have seen with another technique. And I think that's still in process. So that's a long time, right? So you guys probably know I work for Google, but specifically I work for Calico. Calico is a biotech company researching aging, trying to understand why people die. And unlike many of my colleagues, I plan to die. And so if you look at more than 8 years to do one cycle of innovation to impact, and then you look at my expected lifespan, I can divide. What do I get, 4 more of these before I die? It's depressing, right? So what do we do about that? And so you guys know the traditional approach is after your postdoc, you go get yourself a lab, if you're lucky, and you parallelize. You do these slow cycles of innovation and impact, but you do a whole bunch of them at the same time. You take credit for other people's work so that you don't feel so depressed about how little you're going to accomplish before you die. And so, I'm super psyched to be a principal investigator at Calico Labs, best job I've ever had in my life. And I'll tell you a story about Alfred Millett-Sicking, a colleague I'm lucky to work with here, on that kind of parallels that first story. It's attempting to be a strict improvement on a proven useful technology. But the theme of the story is, can we do better than 8 years? All right. So just, again, real quick review. You guys know transmitted light. I'll show you what things are shaped like. Point of fluorescence microscopy is to give you clues what they're composed of. But then, if we're looking at living cells and we're looking at dynamics, so 3D fluorescent time-lapse imaging, that's how we'll look at living cells exploring their environment. And you guys probably know that in most cases, not all, but in most cases, the way you assemble a 3D map of fluorescent distribution is a series of 2D measurements. And in my opinion, and I don't think this is very controversial, the best way to acquire these slices is via light sheet microscopy. So this cartoon shows 2 microscope objectives. One of them is the collection objective. So it's got a thin plane in your sample, which is in focus. And the idea of light sheets is beautifully elegant and simple. You just match the shape of your illumination to the shape of that image plane. The idea being you don't do any damage except at the regions where you're looking. And this is great for reducing photobleaching, photodamage, phototoxicity. And I'll say something that might be a little more controversial. The worst way to collect 2D slices is via point scanning microscopy. So instead of interrogating a full sheet, a confocal microscope interrogates a single point. So the volume is a millionfold smaller compared to a light sheet, but arguably much, much worse. The photodamage is orders of magnitude worse. Just for simple geometry, there's an entrance wound and there's an exit wound. So here's a pair of time lapses from the Schroff lab. The one on the left is showing a light sheet microscope. And I'm not saying there's no photodamage, but you could say that the cell is arguably closer to steady state. Whereas on the right, there's profound photobleaching. It's just undeniable. And photobleaching, in my experience, I think everyone's experience, goes hand in hand with photodamage and phototoxicity to the creature. So even if you could extract insight from these images on the right, I think you should be very careful choosing to believe that this represents a biologically relevant observation because you're roasting the creature to death as you're taking these pictures. So anyway, gentler is probably better. I think that's a fair statement. So if this is true, then you might be surprised by the very true assertion that confocal is still orders of magnitude more popular than light sheet. it's not because people are stupid. This is a rational decision based on a simple technical reality. It's just the interface. There's a huge set of experiments that it's really nice to do them through a cover slip. So my colleagues at Calico, tons of my colleagues here want to use microfluidics to look at really long-term imaging of living creatures. And the PDMS layer and the punches mean you can't come from above. You got to go from below through a cover slip. Everybody who's not doing long-term imaging is doing high throughput imaging. So they want to look through a cover slip because they want to use a multi-well plate. So just because of that, everybody's using a confocal. Nobody's using a light sheet. And this was kind of sobering for me because I was excited to work on light sheet tech dev when I came here. It wasn't clear that it was going to have any real value if I did. And it's not just me, you know, like all the commercial offerings for light sheet that I was aware of when I made this slide, they all dip. None of them go through a cover slip. So they all kind of run into the same problem. So I told you that so I could tell you this. We're sitting on a recipe. We're building on many innovations from many other labs. See, the whole point of science, right? To stand on the shoulder of the giants, to build on other people's innovations. You know, stack your brick on the top of the wall. So just a technical story now on what are we going to do about it. So here's a cartoon of a microscope. You got your happy little cell sitting up here. The dotted line indicates the plane in the cell, which is in focus. You can see this section of the cell showing up on your camera over here. There's a 90-degree rotation between the two that perhaps is obvious. Here's a cartoon of a microscope objective. There's your immersion fluid. There's your tube lens. There's your detector chip. And there's a pretty cool innovation published more than a decade ago in Oxford, Botcher B. and Wilson. It's a classic paper. And it shows a straightforward recipe for making a virtual copy of your sample. So you guys have maybe seen this beautiful pig illusion. You put a couple, I think they're parabolic mirrors, but don't take my word for it. And you've created an imaging system that produces a very convincing 3D copy of the pig floating in space. You can put your finger through the copy. It's not there. It's just an image, right? I think this is pretty cool. And so remote refocus is basically a really high quality, high resolution version of the pig illusion. So it's a cool paper. What good is it? So for me, the initial value of remote refocus was I can take that copy of my sample and image it with a third microscope. But that third microscope now has this luxury. I can buzz the objective on that microscope as fast as I please, take volumes as fast as I want, 50 volumes per second, no problem. And none of that vibration is coupled to the sample by the immersion fluid. So you can go as fast as you want because of this mechanical distance, yet still use high numerical aperture immersion objectives. So it's pretty cool. Fast volumes, high resolution. One of the things remote refocus is good for. And Alfred and I actually built one of these at Calico and put the plans up on GitHub, just kind of like open source hardware. No innovation here compared to Oxford, but just a concrete recipe. By the way, if you're going to build your own, I strongly recommend you follow this recipe. A lot of people make very natural choices trying to build their own, and the result is not a usable instrument. It's kind of a fun question why. Anyway, I think one of the hallmarks of good ideas is that they lead to other good ideas that build on top of them, and that's true of remote refocus. So the next year, Dunsby, brilliant guy as far as I can tell, comes up with, I think, an even cooler idea that gives you a light sheet microscope that goes through a cover slip. So it's pretty straightforward to deliver a sheet to your sample and bend it over. But Dunsby's innovation was recognizing that this third microscope here can look at the pig from a different direction. And what's cool there is if you tilt your third microscope, you can get your focal plane of your collection objective to match the plane of your illumination sheet. And that's the requirement for light sheet microscopy, right? Just showing you the pig illusion, it still works if you look at the pig from a different direction. And that's kind of the essence of this idea, right? So like most beautiful ideas, this one runs into a really annoying, mundane obstacle, which is just the objective, the lenses that you want to use to do a really good job with remote refocus. As you start tilting, they just crash into each other. So it seems trivial, but it's really annoying. And so the way Dunsby surmounted this was very reasonable. He just used lenses with a longer working distance so that the lenses didn't bang into each other when he tilted. It was a great, very practical solution. Now, it comes with a cost. When you extend the working distance of your lenses, you reduce the numerical aperture of your lenses. So the resolution and the light throughput of the system suffers. But in exchange for that trade-off, you get to tilt your third microscope, you get this beautiful tilted image, you get single objective light sheet. I think this is clever as heck. I've always loved this paper. But I do want to emphasize this is a trade-off. You're throwing away a lot of your light. You're throwing away a lot of your resolution. The effective numerical aperture is a very small fraction of what you started with. So it's a brilliant idea, but it's a trade-off. The theme of my talk, of course, is finding the loophole so you don't have to make the trade-off, right? So a brilliant idea, a decade later, came out of UCSF, Bin Yang and Bo Huang. Their idea is for this third microscope, use a water objective. Now, it seems kind of silly because your sample's floating in air. But they put a cover slip inside of the sample, which I think is kind of clever, inside of this virtual copy of your sample. So the poor pig's got a piece of glass through his middle and water all past his waist. And it turns out the effect of this is you can collect from a much wider angular range, much higher numerical aperture, right? Better image quality. So when they tilt, they still throw away some light as they tilt, but way less than the Dunsby design. I thought this paper was awesome, and Alfred and I read it, and it kind of changed the course of our research program, and we decided, oh, we have to build on top of this. This is a great idea. Now, it still has some flaws, of course. The geometry here meant that they had to use a pretty long working distance objective for objective 2 over here. And it turns out that is a limiting aperture on the system. But it was nice because it left something for me and Alfred to do. So what we added was pretty a straightforward extension of the UCSF innovation. We just swapped out the water lens for a lens that used glass instead. So here's a picture of it. We called it the AMS AGY version 1.0 objective. And then on Twitter, we call it Mr. Snouty. There's a shaved snout here. And that's really just for mechanical clearance. It's really just to help solve the problem of collision. So as you tilt this third objective, this shaving just helps you not bang in to the second objective. But I want to emphasize something. This objective is a glass objective. So it's kind of like a turf objective, right? And you guys know when you image with a turf objective, the turf objective might be an oil objective imaging into a water sample. And if you go off the cover slip, you have this big index mismatch. If you go off the cover slip, you get hideous depth-dependent spherical aberration. So turf objectives are great for really high-resolution imaging right on the cover slip, and they're terrible for imaging deep into the sample. The cool part here is this glass surface is our, high index, low index interface, and we put it inside of the pig. Because remember, you're always at depth equals 0 because you can put your objective right through the pig. So this was great. Very straightforward extension of the UCSF stuff, but with some really nice technical consequences. I just want to emphasize where the light goes in is still the normal part of the objective. This shaved surface is optically irrelevant. I've clarified this on Twitter because I think a lot of folks thought this was more sophisticated than it is. But that's it. With this shaved snout, you can pretty much tilt, as far as we can tell, basically losslessly. And then I should emphasize our innovation, building on top of Bin Yang, Bo Huang, Chris Dunsby, Botcherby, and Wilson, also built on top of Bouchard and Kumar and Yang. They've all got this brilliant scanning method that lets you take volumes just absurdly fast. So my assertion then is that this is a bold assertion. You might disagree with this, and that's fine. But let's just pretend this is true. This is the first light sheet microscope with no drawback. If you're using a confocal, you should just use this instead. If you're using a 2-objective light sheet that's dipping, you should just use this instead. Let's pretend that's true, and I do believe it is. But same question, right? Okay, that's true. How long until it matters? What did I learn from my time as a postdoc? So you guys remember what I said about good ideas. What's the most important thing you got to do with a good idea? And the answer is tell everybody. Because if you don't disclose your innovation, how could your innovation possibly have any impact, right? And, of course, we worked really fast to, we went a little faster than I did at the NIH because Alfred's awesome. Got our first images, but here's kind of where we differed. How can you possibly tell if your idea is good? And the answer is it has to get into other people's hands. So instead of following the traditional journal path of making, a bunch of glossy 3D time lapses and surface renderings and fly-throughs and attacking sexy biological questions, we took the bare minimum data we needed to convince ourselves of the scientific validity of our physics claims, and then put the information up on GitHub and tweeted about it. And that might sound silly. And I love Nature Methods. Rita Strack is brilliant, incredibly productive. Nature Methods is a great journal. But if you look at the time to impact, sending my innovation to Nature Methods represented a profound net negative for the progress of science. So we decided this time that the journal not just didn't add value, it actively subtracted value, not just in slowing the dissemination, but in even changing what we chose to share and how we chose to share it. We chose to share as much as possible, as fast as possible. As soon as we were confident it was true, tell the world. Now you guys hear me trashing journals, right? What about peer review? We need peer review, and I couldn't agree more. I think the concept of peer review is beautiful. I think our implementation of peer review, our tradition of peer review, is profoundly suboptimal, which is what I say when I mean something's really stupid. The idea that I think deeply about something for 2 years and some anonymous person thinks about it deeply for 2 hours, writes something, some thoughts about it. We have 2 iterations of written communication. The idea that that establishes the scientific validity of my claims is ludicrous. Reto Fiolka establishes the scientific validity of my claims, right? So I said, we told all our friends, Reto's our friend. Reto had a working instrument in his microscopy lab, taking beautiful time-lapse images of living cells months before we did. Best possible reproduction turned out to be collaboration. And I mentioned before that dissemination often requires kind of a commercial partner. But how does a commercial partner have the confidence to step into a space? Because we released all information as quickly as possible, as publicly as possible, other people around the world could participate in the science with us. And that kind of distributed participation de-risked John Daniels from ASI. He felt comfortable stepping in and commission a batch of, I think it was 25 of these custom lenses. I think we had something like 40 labs lined up to get one of these lenses, to build one of these microscopes of their own, basically a month after we tweeted it, which is absurd if you compare that to 2 years after I had the ISIM innovation, which I think was, in the same ballpark at least. There were 2 of these instruments in the world. By the way, all 25 of those first lenses I think are sold out. I think they commissioned a total of 50 now. And I think, we'll get there. But point being, man, this is faster. Just a couple examples that I really like. So Reto and Kevin and other folks at UT Southwestern are awesome. So they got these beautiful time lapses of their system. They get a nice preprint out that I think is great. They were very kind and included us on the offer list, but this is their work. The BioHub, Chan Zuckerberg BioHub's got a great version of this. Oh, by the way, it was so pleasant for me, since we were lucky enough to build on Bin Yang's work, so pleasant for me that he was gracious and built on some of our work in turn. That really makes me feel good. And just the emotional side of science. This is the life I want to live. Doug Shepard at ASU is spectacular. There's something on Twitter about it looks like he's imaging samples that are like cubic centimeters at incredible resolution for, spatial transcriptomics. I saw some tweets that there's one of these in Oslo and the movies look beautiful. One at UC Irvine that I'm pretty excited about. And this is just a sampling, right? So, I got to tell you, my favorite collaboration, of course, Lockie, I believe, is in the audience. Lachlan Whitehead, who I hope you all know from Twitter, and if you don't, go follow him. Lockie, I apologize deeply for how I've butchered this animation, but it didn't start at the start. Here we go. Very good. So Lockie made this beautiful explanation of the principles of the instrument. I've sped it up and I've trashed all the pixels, but if you go on Twitter, you can see kind of as Lockie intended. But the fact that we were able to have this collaboration is because we were doing this, open science stuff. Lockie ended up on the author list of the paper, which I don't know how I would have done that with a traditional journal, right? Anyhow, and then just kind of a closing word on preprints. So I actually don't use preprints. I just put stuff on the internet when I want to share it. But I got to say, I love preprints. I appreciate preprints. Concrete example, I told you we built on Bin Yang's work. 15 months passed between Bin Yang's preprint and Bin Yang's traditional journal publication. Alfred and I read his preprint the same month that he shared it. It changed the course of our research. It accelerated our productivity tremendously. We owe Bin so much, and Bo, for choosing to preprint. Saved us 15 months. But I was hanging out with Bin, once the smoke cleared, and asked him, I said, hey, you saved me 15 months, but let me ask you, how long passed in between when you had the idea, which is all I needed to change the course of my work, and when you preprinted the idea? And he says 12 months. So think about that. Iteration is how my field works. We all build on each other's innovations. An iteration that could have taken 27 months, took 12. That's great. Thanks, Bin. Thanks, bioRxiv. It could have taken 1 week. if we had a culture that incentivized open, productive sharing, and we don't. And that's what I'm here to do. For my field, and maybe for yours in some way, there's some types of information that really are valuable the moment you have the idea. And that's the culture I'd like to live in. And that's what I'm trying to move towards. And maybe other people want to move with me. The moment you have useful information that you're confident is accurate, you're not trying to, give people bad information or, quality control is the responsibility of the individual. But when you have some useful information, why don't you share it? Here's one of my favorite stories on this topic. So I had the privilege of visiting Ilaria Test, a great lab in Sweden. And I was hanging out with her brilliant grad student, Andreas Bodin, and we were talking about this same light sheet microscope. And I was telling him how actually the worst part of it to build was the scan unit. The scan lenses are expensive. They have lots of optical surfaces, so they're kind of inefficient. It's the most annoying part of the system to align. There's no innovation here. This is an old technology. This subcomponent is an old technology, but it's the hardest part. And he says, my favorite sentence, he says, well, why don't you just, and he goes to the whiteboard and he draws a all reflective version of this scanning system. And I spent a minute arguing with him before I realized he was right. Brilliant invention. The best kind of invention. Why don't you just? So here's a little animation of the idea. The idea is you bounce off one rotating mirror, a galvo mirror, let's say, and then you have a set of static mirrors. And the effect, if you come back to the original rotating mirror, you touch it twice, the angular deflections cancel. You get the pure lateral deflection, which is what we need. All reflective, way more efficient, way easier to align, way cheaper. This is beautiful. So we call it the Scandreas to embarrass him and to credit him. And but he had kind of a funny moment. He says, oh, this is a useful innovation. I said, yeah, there's 5 people I know right now who are building a light sheet right now that should build it with your system instead of the typical system. I said, but I can't tell them because it's your innovation, not mine. And he says, oh, well, I should write an article. And he thinks about it. Okay, so I have to set my current project aside. I have to spend a couple months building the instrument. I have to attach it to a microscope. I have to attach the microscope to a biological question. I have to establish the utility and the validity of the technique. I send it to a preprint server, and then you can tell people. So what's that, 6 months? And the project you'd have to set down as a good project too. And all we wanted to share was this little diagram on the whiteboard. So Andreas, he really stepped up. He says, you know what? Just tweet it. So, we built one. We established that it worked. We made a nice video kind of showing how it worked. And we tweeted it like less than 2 weeks later. And talk about iteration times. That night, the night we tweeted it, Maurice Lee in Singapore built one. Reproduction, peer review, verification of claims, 3 hours. Talking about iteration times. How long would that take with a journal? How long would that take with preprints? I want to turn years and months into hours. In some cases, there's no reason not to. So that's what I'll close on. Why can't we always share like this? And of course, depending on your science, there might be damn good reasons, but think about it, because maybe sometimes you can. Is that a good stopping point there, Cynthia?
I think, if you don't have anything more to share, we'll stop there.
Oh, I wasn't looking at the chat. I'm sorry. My bad. Oh, Alex DeMarco used a Scandreas. That's spectacular. Can I tell Andreas? He'd be so happy.
Yeah, sure. Also, maybe Andrew, there is Donna Whalen, who's from Melbourne. She's also building a snouty. So if you want to give a shout out to her.
Oh yeah, absolutely. She's famous, right? She's. I'm very happy to be. It's kind of silly, but I kind of feel like everybody who's building a similar microscope is almost like extended family. So I'm real proud to be in a family with folks like that. You know what I mean?
Yep. Should we take questions at this point? Ian, are you there? Do you want to moderate questions?
I saw Genevieve Buckley, who I suspect is someone I owe a great deal to. Does Yang's method also suffer from vibrations in the water if you move the lens too fast? If you move the lens, you would absolutely suffer from vibrations in the water. Bin used a scanning technique similar to the one that Bouchard and Manish Kumar used, where the moving part is not that lens, but it is a great question. And I think actually the worst thing about the water lens is it's really hard to align without colliding the cover slip with the other objective. It turns out that's actually one of the worst parts. Oh yeah, here's a good question. Why Twitter? This is fun because Twitter in many senses is a garbage heap. But I think something that's pretty uncontroversial is even if Twitter is a bad mechanism for communicating scientific information, I think just a regular website is great for that, or a conversation like this. But Twitter is an excellent venue for communicating the existence of scientific information. It's a great place for advertising. And the cool part is, at least my network on Twitter is highly enriched for microscopists. I don't follow politicians. And I find I actually stopped using Google Scholar and I stopped using PubMed because I get most of my scientific news from Twitter, and it's actually great. I don't know if that's a satisfying answer for you. Oh, sorry, I saw that I should shut up and let people ask.
There's Niall Gilhagen who wants to ask a question. Niall, do you want to go ahead?
Yeah. Hi, Andrew. How you doing?
Good, and you? Nice to see you.
Yeah, good, mate. How does the king snouty stack up against the baby snout? You know, resolution, performance, etc. It seems like a really cool sort of extra innovation there.
Thank you. I really appreciate you saying that and asking that. So our intention was to make something which was strictly better. So the first one we made, we just wanted to show that the idea was any good, and so there's a certain amount of risk we could tolerate. So you know, it's this big. The field of view is a couple hundred microns. So big snouty. The idea is the field of view is like, I don't know, like 4 times bigger. But the whole point was that no optical drawbacks. So same resolution, just a strictly bigger field of view. The price you pay is it costs more.
Yeah.
Oh, and actually, this is I think you know this, but we're actually kind of at a critical moment right now.
Yeah.
So
Yeah,
you get it. Okay, the big version is snouty with the big field of view. ASI hasn't decided whether or not it makes financial sense for them to risk commissioning a batch. So the more people contact them and communicate that they're eager to purchase something that might cost, like 50% more. Actually, I don't know how much more. Talk to John Daniels. If enough people contact them, they can go ahead and commission a batch, which would be great for me. I'm not making money off that, but if they commission a batch, then I can get those lenses so much more conveniently, and it just makes me happy too. Sorry, Fred.
Yeah, thanks very much. No, that's kind of one of the reasons I'm asking. It's I noticed you were at that critical point. It'd be really interesting to see it.
Oh, thanks,
man.
I really appreciate it. And if you're personally interested, please hit up John Daniels if you haven't already.
Cheers. Thanks.
All right. Next is Patrick Voigelis. Yes, Patrick, go ahead.
So my question was on using Twitter. Obviously, you've got an established network, but what's the chance if someone's just starting out and they use the sort of hashtag microscopy? What's the chance that their idea would get picked up on?
Yes, this is an excellent point. So I was not on Twitter until a couple years after I came to Calico. So right around when I was trying this new approach to sharing, I didn't know how to do it, and I definitely didn't think Twitter was the right way. So you guys might know about the Confocal listserv. It's this pretty old school network of core facility managers and technique developers. And honestly, my initial plan was pretty much just cold calling people, just find people I respect and send them emails telling them about the existence of my work, just hoping to have a conversation, which actually has been pretty fun. But then I tried out Twitter. I logged on, and what I did was I knew I had no network. I knew if I tweeted, everyone would ignore me. Whether my ideas were good or bad, it just wasn't going to show up on their screen. So I contacted some folks I respected who seemed to be, intelligent and with big followings. And I just asked them very nicely. I said, hey, I have something that I'd like to share that I think is worthwhile. Would you do me the favor of, having me as a guest in your house? Can you retweet my stuff? And it turns out just cold contacting other scientists and asking them nicely. And by the way, I'm volunteering. So I don't know if 4,000 followers is a lot or a little, but you are welcome to my 4,000 followers if that's useful for your open science efforts. You follow me? Did that touch your? So it's still a social game, Those and that might be a nice thing about journals is you only have to convince 4 people. You don't have to play the more complicated social game of interacting with hundreds of people. I don't know, high follower count. That's enough. That's enough. Everything's a social game at some level, and Twitter is one of them. But it happened to be one that I found fairly pleasant to play, and I'd be happy to help anybody who wanted to help me the same way that I was helped by others. Did that actually touch your question?
Yeah, definitely. Thank you.
Thank you.
Next is Ian Smythe. I'm just gonna enable this audio. Yeah, Ian, you want to go ahead?
Thanks, mate. Yeah, can you hear me?
Yep.
Yes.
Yeah, no, I'm interested. I mean, you know, I think the arguments around roadblocks to dissemination of information through publishing are really well made, and you know, you've shown how powerful it can be if you get past that. I guess in terms of microscope construction, you mentioned a few times, you know, having to generate a certain number of orders for a snout here and that sort of thing. Do you think that sort of thing is going to hold you back to a similar extent? And is there a different way of funding those sorts of, I guess, hardware innovations?
Now, okay, this is good stuff. This is good stuff because ASI stepping in as a commercial partner was great for us for a bunch of reasons. And one of them is we didn't have to take a financial risk commissioning a large batch. I could definitely imagine a network of scientists teaming up to commission a large batch because the unit price drops off a cliff as your batch size goes up. You know that. If ASI hadn't stepped in, it might have been a fun game to try to find 5 or 10 interested colleagues and go in on a bulk purchase. It's funny you mention it though, because one of the things I'm struggling with right now is, Chris Dunsby's beautiful invention, the Scape beautiful invention. Those are both patented, and those patents are exclusively licensed to Leica. So to me, it would make perfect sense for Leica to include our innovation in their product, and for whatever reason, they haven't chosen to. So, and because they have exclusive licenses on the patents, that kind of freezes everybody else out of the game. And I understand the law, I understand how and why it works that way, but it still makes me sad. So the solution to that game is sort of a combined social technical one. Either work with Leica to help them make a decision that I want them to make, or invent around them. Which is rude, but if we got to do it, we'll do it. Sorry, I wandered off topic though. Did that touch? What kind of stuff are you thinking of?
Yeah, no. I was thinking of exactly that sort of thing. But trying to collect enough people who. So, for example, if you had some sort of way of funding development of new hardware, which didn't necessarily rely on commercial providers or maybe utilize them. And you can see how IP around different lenses or hardware could block things for extended periods of time if a company decided not to go forward with that particular innovation, even though you might see the way forwards.
You might be, I bet you're familiar with the Betzig and Gokul and the Mosaic movement, and they've done an incredible job kind of templating one version of what you might be talking about, where they coordinate with vendors to make bulk purchases, or they coordinate bulk purchase prices, but for kind of distributed labs. I think it helps if you have the Nobel Prize and a whole bunch of science papers. But you follow me? What I'm talking about? Yeah.
Oh, interesting. Thanks.
Yeah.
Cool. And the next one is Cam. Cam, do you want to go ahead?
Yeah, sure. I put in the chat, but I mean, I guess this for hardware is great going out on Twitter and everything. But I mean, how about it for software? I mean, you mentioned you're not necessarily a fan of GitHub, and I'm not either, really. I mean, how do we get things out to people that aren't coders, that don't live in GitHub and all that sort of stuff? I mean, we need some sort of shiny, nice way of getting this across to people.
Yeah, I do less distribution of software, so I might be less qualified to answer. Actually, I bet we have some folks in the audience who are far more qualified than me to answer. Genevieve, are you, or Juan, are you, would you enjoy answering that question? Or other folks who I should have said if I said the wrong folks just now. I don't know. Is that practical, Cynthia? I don't know if I should bounce back to the audience for answers.
Well, I've just unmuted Genevieve, so if she wants to,
perfect.
You can go ahead.
Beautiful.
Hi, can everyone hear me?
Yes.
I don't know, this feels a little weird. I feel like Cam and I probably have the opportunity to talk about this by ourselves. I don't know. I think GitHub is definitely very dominant for doing open source coding work, and so you probably want your stuff on there. Ideally, you want your stuff on there even before you've hit your first release. I think is certainly really helpful and really changes the momentum of projects. We have projects in our lab where that's not the case. Things are in private repos until the paper, or at least the preprint, is out, and there's kind of a noticeable difference in the momentum between those sorts of projects and the other stuff that I do work on that's open source, but just because there's a lot more people who are working on that sort of stuff. So that's, I think, like one way to share it, but it's not the dissemination sort of question that Andy's been talking so much about. And so I think that Twitter is still maybe a useful way of doing that sort of stuff. I don't know. I'm kind of interested to hear about like why Cam doesn't like GitHub quite so much, and like what the kind of challenge that he wants to avoid is about that. Maybe you can put it in the chat or something like that.
Am I still unmuted?
Yeah.
Yes.
Okay, cool. I just find it confusing a lot of the time. Like to just, if I go, oh, someone's got something, I just want to go and click on something, get it down and have a play with it. And to me, I mean, I'm familiar now with GitHub, how it works. When I first hit it, I went, holy crap, what is this? So
Yeah.
getting it out to people that could potentially just shove it on their work and give it a go, they're going to look at that mess of GitHub or whatever other repository you're using and just go, I'm just going to worry about this until maybe some company makes me a shiny front end and I can press go.
Yeah. Okay. Yeah. No, I agree with you. That is really annoying. I think maybe what is the most helpful then having kind of distributed tools that have installer packages with them. So if you're using Fiji, lots of people do, and somebody has like a plugin for it, there's already like that distribution pathway, and people, even if they don't use GitHub or don't do any coding, they kind of understand which things you need to click in order to like get that plugin and actually just run the thing. So that's hugely helpful. I do a lot of stuff with Python, and that is not very nice for people who aren't also Python programmers, because a lot of the time what you need to do is like set up something like Conda, just have a lot of base knowledge even to just install a thing. One of the things for the Napari project that Juan has also been doing like a lot of stuff recently on to do with packaging, has been working out how we can bundle things for people who don't do any kind of coding and they just want to be able to like download an executable and install it and be able to like run stuff immediately. And we've been using Briefcase to do that, which is kind of like an abstraction layer for Python projects between what you would need for things like Windows, Mac, and kind of Linux packaging solutions. But it's been actually like really challenging. So I think, yeah, we just need like more kinds of situations like that where there's something that's like an established pathway for getting a plugin out or getting this kind of thing into the situation where you can just double click and download the thing and then have it install. We're a pretty long way from that just now.
Juan, you're also unmuted if you want to talk now.
Yeah, I mean, I just want to say, yeah, Genevieve, I think, hasn't really expressed how hard she's been working to get a bundle to install Napari. Yeah, it's really hard work. And I think it's work that's not really rewarded in academia. And I think, yeah, that needs to change basically. But yeah, so, if you go to the Napari chat, you will see a lot of back and forth with Genevieve trying to get our distributed builds working. Yeah.
Hopefully when we have it working though, it will mean that other people can contribute in a much easier way. Like once.
Yeah, I would say that is the goal, Cameron, is to not have, we don't want biologists to have to go to GitHub to download our software. And yeah, we want to make that easier for everyone.
That is a disadvantage though. Like you said, it's been a lot of work even just within our own project. And so I think it will be really high reward once we get that working smoothly. But it does make me kind of think more broadly about the rest of the ecosystem and other Python projects that I might be working on. Like sometimes I'll do a thing with PyInstaller, but it's, yeah, a larger problem as well, I think, even beyond our own project.
Just a small mundane technical point on that topic. So in addition to the default GitHub interface, you guys are probably aware of, well, of course you guys are aware, but somebody in the audience might be unaware of GitHub Pages, which is a way to expose the contents of a GitHub repository as a more traditional web page. And that's actually how we publish. I sent a link to the chat that just shows an example of that. Our papers, I don't care so much about the venue, but we actually happen to use GitHub Pages to share our papers as part of the solution. And it works great for that part of the solution.
I think Alex Coombs has a question. Alex?
Yeah, thanks, Senthil. And any great talk, really inspiring and different perspectives. My take homes have been holographic pigs, phase horse, bad idea plus a worse idea equals a good idea. But I wanted to come back to your comments and thoughts about lightsheet versus confocal, and how it was frustrating, that lightsheet's an obviously better technology, but people are still using confocal. And part of that is that practical aspect of, can I mount my sample? Can I use it in a multi-well plate? Similarly, with your focus on kind of dissemination rather than publication, and open science versus commercial, in a way, the open science initiative relies on a different type of infrastructure, on people being able to build their own microscopes, and then have that used in a biological context, or in whatever context people are working in. And not everybody has that type of infrastructure.
Yes.
How do you see people kind of implementing these, or smaller institutes, or biologists who don't have that experience accessing this technology?
I couldn't agree more. Those are excellent points, well made. Building microscopes isn't for everyone. I do really enjoy teaching people to build microscopes. And actually, that's where I'm putting a lot of my efforts this month. Is we released enough information for a certain type of person to build their own microscope. Sorry, I just want to give a shout out to Samantha Stebbins in the audience. Just a brilliant scientist. Really happy to see her here. Maybe Robert Jew is also here. He's awesome. Sorry.
Let's focus on you.
Thank you. The folks that can build microscopes, or the folks that are borderline, I'm doing what I can to try to make that on-ramp a little smoother. So we released enough information for Red Ophiolka to reproduce our work, but I'm trying to release more like a detailed protocol, and I actually really enjoy, I happen to enjoy conversations like this, like technical conversations, like a Zoom conversation where we kind of go through building the microscope is actually fun for me. Mm-hmm. More generally than just building microscopes, one of my colleagues here took an open science approach to releasing a plasmid, and the culture of sharing plasmids, I think, is a beautiful example of how that same spirit encounters a very different technical reality, because sharing plasmids is a lot closer to sharing software. Here's a short text document that saves you a lot of time and effort. So the solution is going to have to be shaped by the realities of the field. But maybe answering closer to your question, folks that can't build their own, how are they going to get one? And the truth is, we do have to make a commercial path to this instrument. I would love if it went through Leica, for example, because they have the exclusive license to the people who I built on top of their innovation. So it's only fair that they get some financial reward. But I also am doing everything I can to keep the do-it-yourself world wide open. The way we're distributing through ASI right now, it's for people who build their own. But I'd like to kind of go right up to the edge of what patent law allows, in terms of making things as easy as possible for home builders without actually violating the law. You see what I mean?
Yeah, that sounds like a great compromise.
Solid.
And you want to emphasize on why people still stick to confocals? Is it the practical aspect of the people, whereas it should be the practical aspect for the samples?
Yeah, that sounds right to me. Is that let's see.
Are there more questions? I'm just looking at the chats.
Oh, yeah. Somebody mentioned the processing simulation that came from the Twitter thread. I can't remember the Twitter handle of the person who did that, but this was super gratifying. When Andreas decided to release his innovation on Twitter, I was the high follower count account that released his innovation. It's not my innovation. But in the thread, not only did Maurice Lee build one, a lot of folks came into the thread and did, had technical arguments, which I didn't think Twitter could do that, but it went great. Manish Kumar raised some really serious technical points. Somebody else responded to some of these technical points with simulations and links to code, and that was super gratifying for me. It's like that was the scientific culture I wanted to live in, was the one where we're actually dissecting an invention together and actually making progress together. Twitter isn't like that all the time, but every once in a while, it's pretty cool. And if possible, maybe try to steer into more of that. Oh, Donna Whalen, hey, nice to see you. Toby Bell, beautiful. Yeah, I'm very proud to be indirectly associated with you guys. What else? Oh, Alex DeMarco, yeah. If you reached out to Andreas, that would warm my heart. Lockie, nice to see you. Who else?
Andrew, could you
Hi.
we've spoken about this previously, and it's something that I constantly get emailed about, is the field flatness on the spinning disk heads. It's a pretty common problem, and we've discussed it previously. And I guess this relates to the issues with patents and ownership of technology. With the Yokogawa, I guess we've talked previously about implementing the technology to provide field flatness similar to the Borealis. Could you comment on that? Because I know a lot of people in the audience are some of the people who have asked me questions about it, and it's not really my expertise, but I think
you might be on this particular topic. I think you might be the right one to teach folks. Actually, would you mind taking a first crack, and I'll throw in if I have additional.
Okay, so what a lot of people don't realize is when they buy spinning disks, there's issues with field flatness. So a pixel in the middle is not equivalent to the pixels at the edge. This was actually technology that was pioneered by Spectral, which was an engineering company in California. And they bought out the modification known as the Borealis, and then later on the Borealis Aurora. And this was then purchased by, the company actually was purchased by Andor to implement this in their systems. And it's beautiful, we get this beautiful field flatness. So essentially it's just a modification of the commercial head. But now with all the patents being released on spinning disk heads, there's all this new technology like the stuff that Andy's done coming into the field. And some of them have field flatness corrections and others do not. So I just wondered, Andy, if you could comment on sort of any sort of progress that you know in the field about the Yokogawa head, whether there's any sort of field flatness correction sort of in the pipeline commercially for those systems.
This is, okay, I'm really glad you mentioned this. So I do not have any contacts at Yokogawa for whatever reason. I'm not sure they view me as a friend. I think they might view me as an antagonist, but sorry for whatever I've done to cause that. But I'm super glad you asked, or not asked, but mentioned, because it occurred to me the other day that if you look at the IP landscape, the only IP obstacles to bringing a super resolution spinning disk head to market is basically the IP would be pretty straightforward to secure. I know all the relevant IP and where to get it, and everybody who has it would be willing to share it. And it would just be a scientific investment to design the disk, and then a financial investment to prototype the disk. And then I bet you I could persuade ASI or equivalent, but I think ASI to step in as taking kind of the financial gamble and reaping the financial profits as a result. Basically, I think we can get the super resolution spinning disk head effectively open source. And if anybody's interested in the scientific aspects of that question, please hit me up. I really enjoy working on that with somebody. And if we did, you could buy a glass disk on a little spinning motor mount from ASI, for example, slap the rest of the system together yourself, and you get yourself a super resolution system for, 5 figures instead of 6. You see what I mean? I don't know if that actually, and then the innovation, about the Borealis, we could add that innovation without having to go through Yokogawa. Did that actually touch on your topic?
Kind of, yeah. It's just a common issue with technology or IP being sequestered by a particular company, and then it's a disadvantage to the biologists, right? We're trying to image, and then the systems that we build or purchase as kits that go into our facilities, if they don't have those modifications, it does affect the biology and the results at the end. So the Borealis was a particular example I could think of, and it is still an ongoing issue with spinning disks, that you do have that edge drop off. So,
if I could jump in, Yokogawa's got a uniformizer, which is their answer to field flatness. I don't know if you're aware of that, or you think that it's worse than the Borealis, but yeah, they do have a solution.
I didn't know.
We did try that actually with the system that we demoed up here, and I'm not sure. I'm pretty sure it was on the system that we demoed, but Rob, if he's here, I don't know if he's. I'm pretty sure he's listening, but he might be doing 2 things at once. We still found issues with field flatness in that system, edge drop off. But I don't know. Have you tried that?
Yes,
I have not.
we're working on different scales than you are, so maybe it's a little bit, you know, more relevant to your work. Yeah.
Ian, do you want to continue with that discussion we're having?
Yeah, look, I mean, one of the things I mean, I don't know who else is on the call, but it does sound as though you're preaching to the choir, which is great. But you know, one of the major things, and I suspect the reasons why people are still using confocal and everything else, is because if they sit down at the microscope and it looks weird, or if there's a command line, or if there's something odd there that they don't recognize, they freak out. And you know, everyone probably on this call wouldn't, but I think most people coming in have issues with those sorts of things. And I guess it's kind of an unsexy part of doing this sort of thing, is making an interface which people understand and which they're familiar with. And I guess that's one of the reasons why the major microscope companies do so well, is because if you sit down at a Zeiss and you look at Zen or whatever else, then you can kind of recognize it. So how do you reckon we tackle that? Because obviously you want to get these things out to as many people as you can, and you want people to be familiar with the sorts of things that they're doing on these microscopes. Is that something you give much thought to?
Oh yeah, indeed. Now, so on a very practical, so going back to the NIH. So, you know, I built the optical system for the microscope, and, you know, that's like half the work, right? So building the software stack and the electronics that coordinate it all was tons of the work too. And none of that was innovative, but it's still super important. At the NIH, I had a very selfish motivation for writing a decent user interface, which was every minute I saved myself. You know, it was like one less minute I had to spend training a user, and I could spend moving on to my next project. But at the same time, the interface that I built at the NIH was very specific to that instrument. And it's not like it did tiling. It didn't have software autofocus. It didn't know what a multi-well plate was. It was just the best I could do as a postdoc. And we're still kind of in a similar situation here at Calico. Yeah, we have a huge computational team, but I'm not sure helping out with my microscopes is what they should be spending their time on. So actually, this is kind of fun. I might dig up. I'm not sure I can. We put a lot of work into our software stack. And at first, the work is on getting performance from the instrument, really pushing the hardware to the limits of what it can do optically and mechanically. But after that, then we start to polish the user interface. And my personal nature is I don't tend to use other people's stuff, some exceptions. But so possibly to a destructive degree, we kind of build it all ourselves. I don't think that's for everyone. But yeah, we put a ton of work into not just getting the low level, like the part of the software that talks to the hardware, as solid as we can. But now, actually this month and the next couple months, Alfred and myself are spending a lot of time polishing the graphical interface. And of course, we'll open source all of that. But we're not micromanager. You know, this is super specific to our particular hardware. So I think the answer might be that I don't have personally a great answer. But maybe to turn it into something more positive, usually where my skills drop off, due to open science, is hopefully somebody else's skills maybe pick up at that point. So, you know, we're privileged to use Micromanager on some of our core facility instruments. We actually use Napari as the display for our system. It's the live 3D display, which is kind of fun. You see the 3 orthogonal projections. I kind of want to show that movie, but it'd be some fumbling to dig it up. That wasn't really an answer to your question, but did I touch at least some of the same topics?
Yeah, look, and I'm just a developmental biologist, so you know a lot of this stuff is foreign to me, and I guess I'm speaking for those people who just wander in and they don't want to know how it's built, and they don't want to learn how to use it beyond what would be a simple way of addressing these things, which sounds terrible, but it's really the thing that you need to get past to get everyone using these machines.
Indeed, and we have that. We have a lot of collaborators that fit that description. Brilliant people, just not.
Yeah. And I years ago I used a development microscope, which was a command line Unix thing, and it scared the living bejesus out of me. It still does. But
we did go the extra mile to get, you know, the interface is you have a joystick, you have live display of the sample, you double click an icon to open the software.
Sure, no, I mean, and I'm sure they're great, but I'm just wondering, you know, if I'm sure there's a limited extent to which these things are transferable between different machines or machines that have never been built.
Yes.
But you know, there's a lot to be said for something that looks roughly the same for different things.
Yep.
In terms of your standard usership.
Napari is a nice contender for part of the solution.
Yeah, sure.
And
That's good. Thank you. Yeah.
yeah, cool.
Andy, I wanted to
Yeah.
jump in.
Alex, yes.
Yeah, so relative to the, let's say, the way to quickly give out systems and make sure that companies don't sit on them for, God knows how many years in some cases. So what we did when we developed the integrated light microscope in the FIB, so what I did was the following. So I developed it briefly and I promised it to Thermo Fisher. So they got an early design, but in parallel, I gave it to another company as well, which I know it's, they didn't have any IP, and I don't care about having IP in this case. It was giving it out. So practically what happens is that I got funding from Thermo to develop it because they wanted to be the first, but I also forced them to actually be quick because otherwise there would be a minor startup that would actually, hit them, let's say. And then what I did on top of that is I published it and I gave out the complete design and the software. So, both companies, screw yourself because, sorry, I want to use it.
Alex, I don't. Nobody from the companies are online here, but
I don't have a story that's quite that awesome. I guess the part of my experience which is arguably relevant to that is I do find that exclusive patents are fairly destructive, but non-exclusive patents can be fairly productive, if that makes sense. So like at the NIH, we were very lucky that we licensed the Instant Sim IP non-exclusively. And I'm really glad we did because otherwise Yokogawa couldn't have participated. And I think that would have been pretty tragic. So let's see.
I have a scientific question since I'm here. I was wondering if you say the Instant Sim, when you guys developed it, I mean, that is done, so that takes care of both the excitation side of things and the detection. You got the pinhole basically on both sides. I was wondering, have you ever tried, because there's something that's been in my head for a while, to basically cut a light sheet and just do structure detection basically by spinning very quickly your pinholes and collect your 1,000 images and get a super resolved image, which does where you don't need to actually do any more multifocal excitation because you already have optical sectioning.
Yep. This I think the best answer I have is like, yep, that's a great idea. I have trouble answering this without doing a long. Actually, would you mind expanding on the idea just for a second longer?
So basically, what I was thinking of is, if you think about super resolving your image by using an extremely tiny pinhole, if you just use that pinhole to basically constrain the position of your fluorophore, and let's assume that you have an image and you divide it. You have an image which you are essentially, it's a 3 by it's a 3 by 3 pixels, and then all you do is basically position for each of these pixels another series of 3 by 3 pinholes basically. So what you will get is the probability distribution, the probability of each fluorophore to be present in one rather than the other subpixel. So what's happening is that you get a super resolved image by taking 9 times more images. It's, of course, you're still wasting photons, but if you do this in a relatively smart way, where basically you're actually using beam splitters rather than than DMDs and many cameras, of course, it's not a cheap system, but practically you're not actually throwing away your photons against the pinholes, but you're actually throwing them against a different detector, which is focused on a different area, simply of your pixel. You see where I'm going?
Yeah. No, it's fun.
So I was wondering if you actually ever kind of attempted to go in this direction.
No, I have not. I have a couple collaborations that are in that same flavor, but I blab my own stuff, but I try to keep my collaborators a little. Sorry. It's annoying for me to. I apologize for the non-openness of my science on that particular topic, just because it's it's other people's stuff in addition to mine. But it's a fun question. Maybe privately, it'd be more fun to discuss further.
Let's have a chat.
Solid.
Yeah,
actually, just to everybody here, if anybody sends me a Google Calendar invite, I will probably accept it or move it to a later date. So if you want to, I don't really answer email, but I show up for Google Calendar invites.
Yeah. Cool. Alex, we can discuss this separately with Andy. Andy, we also talked a little bit about this on the big snouty, where we want to have lightsheet, but the detection should be an ISIM-like module, right? So
yep.
We should have a chat about this later. You want to pop up something and show?
Can you guys see that I'm showing a very awful GIF right now?
Sure can.
Yes.
So the GIF I'm showing, I actually created it with FFmpeg as I was trying to answer other questions. So maybe that's why I sounded a little lobotomized for a minute there. So the GIF is garbage, but it's just trying to show that like this is a user interface for our microscope. Is like hand on the joystick, 3 orthogonal projections on the screen. So you're collecting a stack, but the user can't process that. So you have to show them, X, Y, X, Z, Y, Z, so that they can navigate around productively. And Napari is the heart of that. So that wasn't really an answer to that software question, but I figured it would at least make the Napari folks proud. Sorry for the distraction, but I figured that was fun enough that
it does. I screenshotted that, Andy.
Beautiful. Awesome. All right, so back to.
Cool.
Okay.
All right. I think we are running out of time here. It's been 1.5 hours. Andy, thank you very much for the time, the presentation, and your patience in answering all the questions. It's been fantastic to have a very dynamic interaction post the talk. Thank you, audience, for attending. Next session will be on November 18th. Erdinç Sezgin from SciLife, who does a lot of STED microscopy, will be presenting. If you want to hit up Andy, I think he's on Twitter, as you probably guessed, and you can send him a calendar invite. All right. Thank you very much. Andy, do you want to catch up later with me and Alex over that? And we'll send you a calendar on that, right? And I'll send you the emails that we talked about. So,
awesome.
Also, we recorded your talk, so this talk would be available online. We sent you a form because everything needs a form to be open access. So if you could please sign that and send it back, it would be awesome.
Very good.
All right, I'm gonna close this.
Thanks very much, Andy. Much appreciated. Brilliant talk. Thanks, Senthil.
Thanks, everyone. I really enjoyed this.
All right. See you later, Andy. Bye.